so let us begin once again with the recap. Okay. Slightly longer recap. Okay, so we have been talking about this finite field with q elements. Q is p to the power m, okay, and we know it can be written as so on alpha power q minus 2, right. There is one primitive element, alpha is called the primitive element, okay. So, the multiplicative order of alpha is q minus 1, that is the property, and what else do we know? So, alpha power q minus 1 is equal to 1, and then there is a primitive polynomial pi of alpha which is in fp alpha, right, and the degree m, it is what is called as primitive, okay, and in this field pi of alpha would be this is 0, okay. So, that is one of the properties that alpha satisfies, okay. So, once again do not ask what is alpha, alpha is something which has all these properties and lets you do computations with a field of q elements, okay. So, it is all tied in together like that, okay. And then the latest thing we saw was this notion of a minimal polynomial, okay. So, we defined the minimal polynomial as something. What did we define the minimal polynomial to be? Okay, so, if I have a beta in fq, okay, I know for sure that beta is a root of what? X to the power q minus x, which is a polynomial with coefficients in fp, okay. This is true. So, I know there is some polynomial with coefficients in fp for which beta is a root. The question that the minimal polynomial tries to answer is, what is the minimal polynomial of alpha? Polynomial of beta, okay. So, we need a notation for it. So, I will simply call it as m beta x, okay, capital M for minimal, okay. M beta x is the polynomial of least degree in fpx such that what m beta of beta equals 0, okay. So, there was a point that Avinash was making that this does not quite uniquely define it, okay. Why does not it uniquely define the polynomial? Okay, so, I could take this m beta of x and multiply it by some element from fp, okay, say 2 or 3 or something, okay, then I would still get a polynomial of least degree with this being with beta as a root, okay. So, you have to say something about the leading coefficient, okay. So, very standard thing to do is to say that this polynomial is monic, okay. So, that also should be there, okay. So, monic is part of the definition. What does monic mean? The coefficient of the maximum degree term is 1, okay. So, that is the idea in this monic, okay. So, there are a lot of interesting properties for m beta of x. So, some properties I wrote down. M beta of x is irreducible, okay. So, that is the first property. It is irreducible because if it were to be reducible, then you can write it as a product of 2 factors at least, and then beta would be a root of one of them, okay, at least one of them, and then that would be a polynomial of lower degree which would violate the least requirement. So, that makes it irreducible. What else did I write down? I must have written down some other property, no? Okay, so that is something we will come to later, okay. So, this okay, so let me write that down, okay, then we will proceed, okay. So, we wrote down in fact an explicit formula for m beta of x. Okay, so this is going to be product of gamma conjugates of beta x minus gamma. Okay, so what are the conjugates of beta? It is basically this set beta, beta power p, and then you raise beta power p to the power p. So you would get beta power p squared, and then you would get beta power p power 3, so on. Okay. Eventually of course this will repeat, so wherever it repeats you just simply stop, you do not include the repetition also into it. Okay, so it will come back to beta once, so you stop wherever it repeats. Okay, so that's the way you define conjugates. Okay, so I promised some kind of a pseudo proof for this result. Okay, so it's the basic idea is to show. So I'll just simply sketch the proof. I don't want to write down a proof. Like I said, the books I'm sure will have a proof. You can go look at it. I'll sketch the general idea, so you'll get how it works. So the basic idea is to do something like this. You can show m beta of x, okay, whole thing raised to the power p would work out to m beta x power p. Okay. So it's not too hard to show when you raise this to the power p. Okay, so something like this will happen. P is, when you can think of, when odd or even will be some issue to take care of when you look at -1, but p is mostly odd, right? Only even prime is 2, and with 2 -1 or +1 does not matter. Okay, so it is all the same. So you can show this quite easily, not quite easily, let me say, with some work you can show it. So once you show this, you can argue from this that m beta of x belongs to fpx. Okay, so the coefficients of m beta of x will be fp. Okay, so that's the main idea. Once you get that, m beta of x has to be the minimal polynomial. Okay, why is that? Because one of the other properties of m beta of x which I wrote down before I came to this was what? M beta of gamma is 0 for gamma being conjugate of beta. Okay. So if you take any power of pth power of beta and plug it into its minimal polynomial, that also has to be a root. That's got to do with the way coefficients of m beta of x. So all these have to, I mean, they're all related. There are some dangerously cyclic kind of arguments here which you have to avoid very carefully, but it works out quite easily to be true. Okay, so there are other ways of proving this, and you will get the answer. All right. So we also checked this by example, and I think for F8 I asked you to check by example, and for F16 I wanted you to do it at home. Okay, I won't ask you to raise your hands if you did it at home, but I believe that at least some of you tried it. Okay, it's a good exercise to try and convince yourself. Okay, so but let's do it real quick for F16. Okay, I know the answer ahead of time, so I'll just write it down without doing too much work. Okay, so F16 is what? Basically a finite field with 16 elements. So you need a primitive element which has order 15, and then you can take any primitive polynomial. This is one of them. There is only one other that you can take for degree 4, but we will just take this one. Okay. So this is F16. So the way you have to do conjugates is you simply start at 0. 0 is very easy, right? 0, what are the conjugates of 0? Just 0, nothing else, and the minimal polynomial is very easy to write down. What is the minimal polynomial? Is x. Okay, and for 1, x plus 1. Okay, plus 1 or minus 1 does not matter because my characteristic is 2 and minus 1 is the same as plus 1. Okay, so this is for 0 and 1. For beginning with alpha, you will have a non-trivial set of conjugates. Okay, so alpha, then what would be the next conjugate? Alpha squared. The next one is alpha power 4. Next one is alpha power 8. The next one is alpha. So you can stop there. Okay, so that you can stop. So these are the 4 conjugates. So the minimal polynomial for alpha will work out as x plus alpha times x plus alpha squared x plus alpha power 4 times x plus alpha power 8. Okay. If you do the computation here, if you multiply, look at what happens to the coefficients, etc., you should get what? X power 4 plus x plus 1. Okay. So, this was done kind of with hindsight, you know the polynomial is alpha power 4 plus alpha plus 1. So, you get the answer quite obviously. Okay. So, it will work out without too much trouble. Okay. So, next what you have to do is you have to look at what terms you have missed out here to find other minimal polynomials. Okay, no point in looking at alpha squared again. Why is there no point in looking at alpha squared again? You will get the same set of conjugates. Okay, so you do not have to repeat that once again. So you can go to alpha power 3. Okay, what would you get next? Okay, so 16 is 2 power 4. So that means P is 2, M is 4. Okay, M does not matter, but P is 2. Okay. So you have to raise the previous thing to the power P, which means you have to keep squaring. Okay. So we will mostly in this course look at characteristic 2. Okay. So don't worry about P being something else other than 2. Okay. So simply take P is 2, always square. Okay. That is the rule to keep in mind, always minus 1 is the same as plus 1. Very rarely will we ever go out of characteristic 2. Okay. So let us say what will be the next one? Alpha power 6, alpha power 9, no. Alpha power 9, but alpha power 9 comes later. Okay, so don't write with so much foresight, you can get into trouble. Okay, so let us do alpha power 12, next alpha power 9. Okay, and then you have to multiply it out. Okay, so if you do this calculation, okay, I know the answer of this calculation, but for those who do not know, it is a little bit more difficult to do. You would get this answer. Okay, so x power 4 plus x power 3 plus x squared plus x plus 1. Okay, so that is the minimal polynomial corresponding to alpha power 3. Okay. So you can check a lot of those things. It is irreducible. Okay, so it is one of those irreducible polynomials. And you have to do some checking to figure out this is irreducible, right. So you can plug in 0, plug in 1, and then you also have to divide by x squared plus x plus 1. Okay, so once you see that none of those things divide, you can conclude that that is irreducible. Okay, what is the next term that I can look at? Alpha power 5. Okay, so what about conjugates of alpha power 5? Alpha power 10. That is it, right. So that is it, only these two. Okay. So now who is going to tell me without doing the multiplication what this irreducible polynomial has to be? It has to be x squared plus x plus 1, right. You know it is a binary polynomial, you know it is irreducible, it has got degree 2 and that just gives you one possibility, you do not have anything else. So this has to work out to x squared plus x plus 1. Okay. If it is not, then you are making some mistake in the computation. Okay. So you can go back and check that. So here is one more thing which is interesting about these finite fields. So if you look at the complex field as an extension of the real field, every real number, I mean how many conjugates can a complex number have? It's either 1 or 2, right. So either it's an element is its own conjugate, in which case it is real, or it would have one other conjugate. So here you are seeing a more interesting situation. An element can be its own conjugate, okay, and then just that is the end of the story, or it can have multiple number of conjugates. You can have 4, you can have 2, all kinds of interesting situations happen in finite fields. Okay. All right. So what is the next thing? Alpha power 7, 14, 13, 11. Okay. So once you do a lot of coding theory, all this the sequence will be automatic. You just know exactly what has to happen, but first time you see it, you will be thinking what is going on. Okay, so it's just 7, 11, 13 and 14 are the conjugates here. Okay, so you can once again do the multiplication. What do you think the answer will work out to? Okay, so Okay, so that is an interesting way of doing this. If you didn't, if you don't notice, you can put x equals x inverse in the first equation that I have here, okay, and then you do some manipulation. You will see that this is basically the polynomial with the coefficients flipped around, okay, inverted. So you will see this will be x power 4 plus, sorry, sometimes this touchpad is a bit little too sensitive. So x power 4 plus x power 3 plus 1. So it is basically, so what has happened between these two polynomials? You put x equals x inverse and then multiplied by x power 4. So what it does in effect is, you have a set of coefficients like this, you are simply flipping it around. That is what that does. Okay, you might have studied some kind of something like this in DSP or something, maybe. It is a simple little operation. It is just this flipping around of things. Okay. So that is it. Those are the minimal polynomials of elements in F16. What will I get if I multiply all these minimal polynomials together? X power 16 plus x. Okay, so you would get that. So that also something we saw in the last class. Okay. Okay. So a lot of curious results are true, which we will not prove in this class. It is not too difficult to prove also, but we won't prove it. For instance, if m is 4, okay, the only degrees of minimal polynomials can be 1, 2 and 4. Okay. So basically the degree of a minimal polynomial has to divide that exponent m. It has to happen. So if you do some computation and you see you got a polynomial, minimal polynomial of degree 3 and m was 4, then it means you have made a mistake somewhere. Go back and check that. It's something you can use in your examinations if you like. Okay. So the degree of the irreducible polynomial you get as a minimal polynomial has to divide m, okay, and there has to be at least one which has degree equal to m also. Okay. So you cannot have m not occurring. Okay. M will definitely occur, and I am sorry,
the pi of alpha itself,
yeah, that itself will come. The primitive, if you used whatever polynomial you used for generating the field, that itself will come definitely. But there is lots of circular logic in using such things, but it's a careful way in which you have to build it, but these are results that are true. Okay. You will get something which is degree 4, etc. Okay. So beyond that, it's really difficult to say what it will be, when you can get some irreducible polynomial. Okay. There are also all kinds of results about, in fact, all the irreducible polynomials of degree m will definitely show up in this list. Okay. So those are also interesting things about what happens in this minimal polynomials. Anyway, that's not relevant for the course, but it's good to know these results. Okay. Yes.
If we multiply all these polynomials, we will get only 14. We won't get x and x plus
1 plus 1, 2, 6, 10, 12. If we did not get x power 16, I made a mistake. Theory is correct. You have to get x power 16 plus x. So I don't think I made a mistake here. It works out correctly. Okay, so let's just stop with this for minimal polynomials. So okay, there's one more result I have to give you. I'm sorry about that. So let's just finish that final result and then we'll go there. Okay. So if you have a polynomial f of x which belongs to fpx, okay, such that say f of beta is 0. Okay. So remember, beta is some element of f p power m. Okay. So if beta is the root of some polynomial with coefficients in fp, okay, then you can show without too much effort that m beta of x will divide f of x. Okay, it's not too difficult to show. You can show using several arguments. One very theoretically appealing argument is to divide f of x by m beta of x. Okay, then what would you get if you divide f of x by m beta of x? You would get a quotient q of x and then a remainder r of x. What will be the degree of r of x? Strictly less than degree of m beta of x. Now what can I do? to claim my result? Put x equals beta. What happens to the left hand side? Goes to 0. What happens to the first term?
0.
Goes to 0. So what should happen to r of beta?
0.
Go to 0. And does that give you any violation? Yeah, it cannot have degree less than degree of the minimal polynomial. So that gives you a violation. This is one way of using the division algorithm to prove it. Another way to prove it is to say if f of beta is 0, f of beta power p is also 0. Okay, so why is that? You simply raise f of x to the power p and you will get the same answer. So coefficients do not change, this becomes x power p. So you can use that to claim the result. F of beta power p is also 0, and then the minimal polynomial is anyway the product of all the conjugates, and all these terms are, they do not have any common factors. So when you multiply it out, it also has to divide f of x. Okay, so that's the way to, that's another way of arguing it, but this is also a neat little argument. Okay. Okay, so this is a little bit crucial because we will use this argument in our code construction. Okay, so we will say, so try to stare at it a little bit and make sure you understand what it means. Okay, so for instance, if I have a polynomial with binary coefficients, let us say f of x is an f2x, okay, and then I say f of beta is 0 for some beta in f16, okay, such that this is true. Okay, here is an example just to illustrate. Okay, say f of x is non-zero for instance. Okay, then what can I say about f of x? What can I say? Is there any information I can get about f of x? Let us say beta is, maybe beta is some, I do not know, beta. So let us say alpha is a primitive element. Okay, so let me be a little bit more specific so that we get something more concrete out of it. It is a primitive element. Okay, so what can be the degree of f of x? It has to be at least 4. Do you see that? Okay, so it cannot have degree 1, degree 2 and all that, right? It has to be degree at least 4. Reason is the minimal polynomial of alpha, which I know is a degree 4 polynomial, has to divide f of x, which means f of x has to be a multiple of that, and that will have degree at least 4. Okay, so this is a interesting kind of idea. If you have one root from a large field which is an extension of your field of coefficients, then that one root means there are several other roots also, okay, from that same field. Okay, it is like saying if you have a polynomial with real coefficients, it has one complex root, then it should also have a conjugate as the root. Okay, but this is just a small extension from real to complex, so you have just 2. But when you go from f2 to f16, there is a large extension, right? So larger than 2 at least, 4. So when you have one root, you can get up to 3 other roots. Okay, depends on alpha. So for instance, if f of alpha power 5 was 0, then it can even be degree 2. You just guaranteed one other. You say, but if you say f of 1 is 0, then it can be anything. Okay, so that's the idea. Okay. So very often we can also use this argument in a reverse way. So suppose I say both these things are true. So what should happen to f of x? F of x has to be of the form some multiple of what? M alpha x times m alpha power 5x. In fact, I should be a little bit careful here. I should say it is a multiple of LCM of m alpha x and m alpha power 5 of x, but the least common multiple is the product because there is no common factor between m alpha x and m alpha power 5x. Okay, so I might as well multiply it out, but in case, so suppose I say for instance instead of alpha power 5, if I had alpha squared, then I can't say m alpha of x times m alpha square of x, then if I do the LCM, it simply becomes m alpha of x. That is the only thing I can say. Okay. So, this notion is used in our BCH code construction. Okay, so, stare at it for a while and make sure you are happy about it. Okay, it can come back and haunt you later if you did not get the true meaning of how you go from a polynomial with coefficients in binary, but having some root from F16 or some other larger field, and what it means about that polynomial. If you have multiple roots from F16, what it means about that polynomial, so on and so forth. Everyone's happy? Okay. All right. So, should I break the suspense and define the BCH code, or should I torture you for a little bit more with some, no? BCH code, everybody wants BCH codes? Sure? I think you are hesitating because you know what's done today is included in the syllabus for the quiz. Maybe you want me to wait for a while, but anyway, so it does not matter. I am going to define BCH codes. Everybody is having second thoughts now, no chance, BCH codes are there. Okay. Alright, so let me expand BCH first. That is the first thing you should do when you do BCH code. First name is Bose, second name is Chowdhury. These two I can spell quite easily, but the third one is difficult to spell, so I might make a mistake. Go back and check with your book. I think this is correct. Okay, so the last part could be my own spelling. Okay, so go back and check that, could be some mistake here. Okay, Bose and Chowdhury are quite standard. Okay, so BCH codes are one of the earliest codes that that showed up, and very interesting from so many different points of view. They are used in theoretical computer science, they are used in coding, of course, in practice and in theory. Okay, so it is a very interesting, elegant, okay, some might even say beautiful construction of codes. Okay, and what else should I say? Okay, let me just define them, then we will do something else. Okay, so a couple of parameters that go into the definition of these codes. Okay, first is the block length. Okay, you know codes usually mean I have to tell you what the block length is, I have to tell you what the dimension is, or basically I have to give you the generator matrix or the parity check matrix, right? Some such thing I have to give you, or I should define the code using some other means. Okay, I will do some 2 or 3 types of definitions to convince you that all of them are equivalent, and then we will finally look at how it works out. Okay, the first is going to be a parity check matrix definition. Okay, so let us say we will begin with an n. Okay, so this there's something wrong with the display, so don't get confused by some balloons coming up from here and there. They are not my work. I'm trying not to do it, but somehow it decides on its own. Okay, so we'll pick n equals 2 to the power m minus 1. Okay, so n is my block length. I'm going to pick it in this form. It's not very special. You'll see later on I can relax this very easily, but for starters I'll start with this, so that the definition is simple and nice. And for this particular n, the code has several other interesting properties which make it very interesting. Okay, so that's why I'm picking this, but there's nothing very special about this choice. Okay, so n equals 2 power m minus 1. What is m? M is some positive integer. Okay, so you take it as positive integer, and then we need this abstract alpha, as you call it. What is alpha? This strange alpha you need for this construction. Okay, so we'll take f in alpha in f2 power m to be a primitive element. Okay, so I'm going to give you a parity check matrix which has entries from f2 power m. Okay, so that itself is a slightly strange notion. Does it really define a code? What kind of code does it define? We have to look at it very closely. Okay, so let's do this. Okay, alpha in f2 power m, and here's the parity check matrix. I'll just give you the parity check matrix and worry about other things later. Okay, parity check matrix would look like this. The first row will have 1 alpha, alpha squared. Let's say I'll put down alpha power 3 also, so on till alpha power n minus 1. That's the first row. The second row, okay, second row is 1. So I'm just thinking if I'll run out of room here, hopefully this, let me just write it first and then draw the brackets. Okay, second row is going to be 1 alpha squared whole squared, alpha power 3 whole squared, so on till, okay, so I think I'm going to write it the other way around. think that is better, alpha squared whole power 3, alpha squared whole power n minus 1. Is that okay? Okay. So, what will be the third row? Alpha power 3, alpha power 3 squared, alpha power 3 raised to the power 3, so on till alpha power 3 raised to the power n minus 1 dot 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 dot. We have to stop somewhere. So, for that we need another parameter. Okay. So, that parameter, it is common to take it as d minus 1. Okay. So, d is some positive integer. Okay. It has some constraints, it cannot be any positive integer. Think of it as a small positive integer, 3, 5, 7, something like that, something small compared to n. Okay. It cannot be very, very large. Okay. So, and we will stop at d minus 1, alpha power d minus 1 squared. Why d minus 1 etc. will become more clear. Can somebody guess why d minus 1? Yeah, so we will be able to later lower bound the minimum distance by d. Okay, so that is why the obvious stop at d minus 1. That is why the obvious notation d for this positive integer. Okay, this dot 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 all the way here. Okay, quick terminology. So, n is called the block length, of course, d is called the design distance. Okay. I am going to define two different codes with this one parity check matrix. Okay, both of them you can call them BCH code, but usually the binary version, one of them is called BCH. So, I am going to first define the binary BCH code. Okay. Okay, so we need a notation here. Okay, so what notation can we use? I will simply say C. Okay, so for now we will say C, later on we will see what to do. C is set of all vectors in F2n such that H C transpose is 0. Okay, so this is the binary BCH code of block length n and design distance d. Block length n equals 2 power m minus 1 and design distance d. There is also a non-binary BCH code that I can define. It is more popularly known as the ReedSolomon code, RS code. Here what would I change in case I want a non-binary code? Yeah, instead of C being F2n, I will simply make it F2 power m n. Anyway, my parity check matrix is defined over F2 power m. Can as well do the codes from that. Okay, so that is the non-binary BCH code or ReedSolomon code. Okay, a very popular abbreviation is RS. Okay, again, so maybe I will put CBCH here just to distinguish between CRS. Okay, so maybe the M should be better spelt. Okay, so first of all notice that this HC transpose is a very well defined operation. There is nothing wrong with that in both these definitions, right. Why is that very well defined? Even though H has elements from F2 power m, I know it also contains F2 inside it and it is a proper extension of that. Okay, so this it properly contains F2 inside it. So I can definitely do HC transpose, right. After all, I know 0 and 1 are in F2 power m also. I might assume that as being belonging to F2 power m and do the computations, no problem there, right. Definitely if I say C belongs to f2 power m also, it is very well defined. We did see some examples for f4, right. In general f2 power m sounds like a very large quantity, but we saw for f4 how these examples work. So I can have a code over f2 power m. So this code is clearly over f2, it is binary, this is over f2 power m, right. The code words are vectors where each coordinate is a symbol from f2 power m, it is an element of f2 power m. Okay. So we will not look at non-binary BCH codes for a while, we will look at binary BCH codes, but some of the proofs are very similar for either of these properties. So I do not have to really repeat each of the proofs separately over and over again. I can just I can simply do one common proof for both, because after all they share the same parity check matrix. For instance, the rank properties that define minimum distance is going to be very similar, it's not, nothing is going to change for those things. Okay. So all those things are fairly critical, fairly similar. So we will do some of the proofs and I will simply say the same proof holds for ReedSolomon also. Okay. So that is why I defined both of them together, but usually in a course, in a book for instance, they would do BCH first and then take a lot of time before they do ReedSolomon. Okay. So you should get used to that also. Okay, so let us stare at this parity check matrix once again. It is important that you stare at it and assimilate it. It is quite easy to remember. Okay. So 1 and alpha square all the way till alpha power d minus 1, and then you square it, then raise it to the power 3 and go on all the way till n minus 1. Okay. Now suppose I picked n to be, let us say 2 power m minus 2 or 2 power m minus 3 or some number lesser than 2 power m minus 1, not equal to that. Can I do the same definition? Yeah, I mean I can do pretty much the same definition without losing too much, right. So that is why I said the n equals 2 power m minus 1 does not matter. Okay. So if because I picked it to be equal to 2 power m minus 1, I can happily write alpha belonging to f2 power m primitive. If it was something lesser, then I have to say how I find the 2 power m, okay, the smallest 2 power m greater than n or something. I have to write that down very clearly, it is just a bit more painful. So I simply wrote n equals 2 power m minus 1. Okay. Another thing you notice is I have picked alpha to be primitive. What will happen if alpha is not primitive in this choice? Yeah, so these columns will start repeating, do you see that, right, and I have gone only up to n minus 1, I did not go to n. If I go to n, what will happen? I will simply get all ones column, which is the repetition of the first one, which means the minimum distance is 2. Okay. So that will just kill everything. Okay. So I can't allow this repetition to happen. So the only crucial property is the element that you pick from f2 power m should have what? Should have something at least n, order at least n. As long as you pick something of order at least n, this parity check matrix would be a very well defined parity check matrix without any repetitions, and it would give you the minimum distance property that we are going to get. Okay. So it is not so what I am trying to say is there are several very simple generalizations right from this definition, but we will mostly stick to this choice of parameters in the proof just because it is simple to write it down, that is all, no other reason. But in general there are other obvious extensions for which the same kind of proof for minimum distance holds. As you can imagine, the most crucial thing is the proof of minimum distance, right, nothing else is important here. As long as you know that there is a minimum distance, you get that. Okay. Alright, so do you want to study different ways of viewing this or defining this code first, or do you want to see the minimum distance proof first? K, okay, that is an interesting question. Okay, so to find out more about k, or right, k is the next parameter of interest, right. What is k? The dimension of the code. Okay, for which of these codes is k very easy, likely to be easy? Just without too much thinking you can do k. First one or second one? Strange. I think in my opinion the second one is slightly easier. Why is that? Yeah, all the elements are from one field. I can do Gaussian elimination to find out what it is, right. So all I have to do is Gaussian elimination on H to find out the row rank of H, because I have a properly well defined code over f2 power m, it just coefficients from f2 power m. So I do Gaussian elimination over f2 power m, I find out if this has got full rank or not. Okay, okay, and if you pick D suitably small, I have not really told you what choice of D is good, but when D is something small, let us say, then this will have full rank, in fact it will always have full rank for many cases, okay. So it will have full rank, and then you can easily find K. Why can I not use the same definition, same idea for the first code? Can I use the same kind of idea? Suppose I find out that this is full rank in f2 power m, can I say n minus k will be D, right, D, right, D or D minus 1, D minus 1 for this, for even the first code, can I say that? F2, right, see that is the problem, because I am saying C is restricted to f2n, I can't allow code words from f2 power m. Remember all my vector space, all the Gaussian elimination works only in f2 power m when I have elements from f2 power m in H. Suddenly I am putting this artificial restriction that the solutions, the null space I am looking for is not in f2 power m, right, it is only f2, okay. So that is an artificial restriction, okay. I have to resolve that somehow, okay. Unless I resolve that I can't be sure about my K, okay. See, this is basically null space of H, right, am I right? Is this the null space of H? If this is also the null space, I do not need two different definitions, right? Both of them would be the same, right. This is not the null space. What is this? This is the null space of H. What should I do to the null space of H to get this? I should intersect it with something. What should I intersect it with? With f2n, okay. So that is an artificial intersection that I am introducing, intersected with f2n, okay. Now this is not a very linear algebraic type of intersection, right, it is not a rank or any row space or something, it is something else I am doing totally different, it has got to do with how the fields work, okay. In fact it has got to do with how minimal polynomials work, okay. So that is why we saw minimal polynomials, to resolve what this intersection does to the dimension k. So that is why we are looking at minimal polynomials, etc. Is that okay? So the first thing you have to appreciate this, the difference between these two definitions, okay. So let us see a very simple example to convince ourselves of this difference at least first, and then we will go on to minimum distance proofs, etc., etc. Okay. The easiest examples come from which field? F4, okay. So right, it is too simple, but anyway, I mean let us just see the example, it does not hurt too much. If it is too trivial, then we will go to F8 and then you guys have to do all the work, okay. So alpha power 3 is 1, alpha squared is 1 plus alpha, okay. So let us define what is the n that I can have here. Three, right, I cannot go 3, can I go up to 3? Yeah, you can go up to 3. Everybody is looking at me as if I made some mistake, okay. So alpha has got order 3, so I can go up to n equals 3, okay. So order n is okay, okay. So the first row would be 1 alpha, alpha squared, okay. Then what about D? Yeah, let me say D equals 2, I picked D equals 2, let me not say. What do you mean you can't pick? I mean I can pick. No? No, you can pick, let us say D equals 2 is fine, okay. So I will say n is equal to, so remember m is 2, I will take n is 3, okay. So alpha is okay, I will take D is 2, so then H has simply only one row, okay. So it is a nice enough thing, I mean you might think it is too trivial, but it is not so simple, okay. So let us say it is just got one row, okay. What is C BCH and what is C RS? Let me see, take some time and try and figure out the code words of these two codes. I mean I want you to write down all the code words, not maybe not all, should I write down all? Maybe not all, at least a few, okay. So for C BCH definitely all, for C RS maybe a few. People are able to quickly answer, okay. So let us see, we will wait for everybody. Okay, for BCH a quick way to do it is to exhaust all possibilities for C. Okay, after all you have only 8 possibilities, right, there are only 8 different vectors for F2 3. Okay, you exhaust all possibilities, you will see only 2 of them will qualify, it will be 0 0 0 and 1 1 1, there will be no other code words. Okay. What about RS? The same?
This union more.
This union more. You really don't want to get any marks in the exams. Okay, so for that you have to do just the proper null space type of operation. Take a look at this. What is your I part and what is your P part? Okay, you can take this to be your I, right? This is the identity matrix. So you have a parity P1 here. You have two messages M1 and M2, both of them from F4. Okay, so you will have 16 different code words in CRS. How will you compute P1? P1 is M1 times alpha plus M2 times alpha square. So that is all, that will give you all CRS. Okay, 16 code words. Is that okay? See, what should you do to find CRS? You have to do Gaussian elimination, right? But here there is only one row. I mean, this is very trivial Gaussian elimination. You can simply go to that one, and you have already done Gaussian elimination. Okay, and you already know what the parity is. You write it down. So you will have 16 different code words. Is that okay? Seems simple enough. Okay. Now the next example. A slight twist on this. We are still in the same F4, but I am going to throw in one more row to this. Basically I am going to pick D equals 3. Okay, remember alpha power 4 is the same as alpha, just keep it like that. Now what will be CBCH, what will be CRS? Now we can write down all the code words for both codes. CBCH remains the same. Okay, so interesting or not? Interesting, slightly interesting. You have to check what?
This set will be contained in the previous one because
you have to do Gaussian elimination doing CRS. Okay, that is the easiest way of doing it. Okay, so let me do it. If you are not too interested in doing it, I will show you how that is done. Okay, so you do first, you do pivoting, right? So you get the first element to be 1 and then make all the elements below it 0, right? So how do you make the element below it 0? You have to subtract, which is the same as adding. Okay, 0, what is alpha square plus alpha? 1, what is alpha power 4 plus alpha square? 1 again. Okay, and what is the next step? To make it I, multiply the bottom row with alpha and then add it to the top row. So that would give you an I right here. Okay, 0, alpha power 3 plus alpha is what? Alpha squared. Remember alpha power 3 is, oh, how did this become alpha power 3? It is alpha squared. Oh my god. That is why I thought something is wrong. This is 1, then what do you get here? 0, 1 and 1. So this is the parity check matrix after you have done row reduction. Okay, why can I not do this row reduction when I am working with CBCH? What was wrong with that? See, the first step I only added the first 2 rows, that was clearly a binary coefficient operation, and then for the next step what did I have to do? I have to multiply by alpha, and that is clearly not permitted if I am only working with F2. So as long as you do only F2 row operations, you are okay, there is no problem. When you start multiplying by alpha, you are clearly going to a F4 row operation, and that clearly violates my definition of BCH code. Okay, I am not contained within the space I defined it to be. Okay, so that is a problem. Okay, so that is why only the RS code is the proper way. I mean, only Gaussian elimination applies only for the RS code definition. Okay, so here the code is easy to write down. You have two parity bits, P1, P2, parity symbols, I am sorry, P1, P2, and then one message bit M, and what is P1? P1 equals M1, P2 equals M1. So in fact, what do you actually have here? The repetition code. So you simply have M1, M1, M1. Okay, so what are the 4 code words? That's it. Okay. All right. So if you want more experience, which I will strongly suggest that you try, go to F8 or F16 if you are really brave, and try the same thing for different Ds. Okay. So you see how it looks like, but of course the number of code words will shoot up a lot. Okay. So but you will learn something. I think something there is valuable if you see it. Write a small MATLAB program which does this for you, etc. This will give you a good idea of what happens. Okay. Anyway, so a couple of quick things that you can figure out just by the definition is, you will always have C BCH contained in CRS. Is that true? This is true, right? So F2 is contained in F2 power m. So clearly C BCH will also be contained in CRS always. Okay. So if you are doing the computation and you find that this is not true, something has gone wrong. Okay. You can go back and check that. Okay. Okay. So before we go to the proof for minimum distance, I want to show you something about k. Okay, so I think it's reasonable that we do that. We have to find out the dimension first before we find out minimum distance. Okay, so I've always been saying dimension of codes are easy, minimum distance is a hard problem. Okay, so we'll do the dimension first. Okay, so dimension. So remember, what was my, let us say, the ith row of H for I between 1 and d minus 1. Okay. What was the ith row of H? 1 alpha power I squared, so on till alpha power I to the power n minus 1. Okay. So this is interesting, it almost looks like x power 0, x power 1, x squared, so on till x power n minus 1, and I am simply putting x equals alpha power I from I between 1 and d minus 1. Okay. So if I think of a vector C, let us say as just C0, C1 all the way till Cn minus 1, which is say in F2 let us say something, let's say F2 power n or F2 power m to the n. Okay, so one of those two things that I would do for BCH codes, this I would do for RS codes. I can associate with this vector a polynomial which is just a formally equivalent polynomial. It would look something like this: C0 plus C1x plus C2x squared plus so on till Cn minus 1 x to the power n minus 1. Okay. This would be a polynomial which belongs to either F2x for BCH or F2 power mx for ReedSolomon. Okay. So the ith row of H is imposing a certain constraint on this vector. What is it saying? It is basically saying, the ith row of H is saying, okay, ith row, I forgot to write row. Okay, ith row of H is basically saying what? C0 times 1 plus C1 times alpha power I plus C2 times alpha power I squared plus so on till Cn minus 1 times alpha power I n minus 1 equals what? 0. Okay. So, let us stare at C of x and the condition imposed by the ith row of h for a while and see if we notice something. What can we notice? So, instead of saying my code word has to be orthogonal to the ith row of h, I can equivalently say my code word polynomial. So, this is my code word vector which has to be orthogonal to the ith row of h. I can equivalently say my code word polynomial should do what? Should have alpha power I as a root. Okay. So, both of them are perfectly equivalent statements, they are just formally exactly equal, nothing more to worry about. Okay. So, basically the ith row of h imposes the constraint that C of alpha power I equals 0. Okay. So, now you will have two different situations for the BCH code and the ReedSolomon code. Okay. So, I am going to branch out, do BCH on the left and then do ReedSolomon on the right. Okay. So, for ReedSolomon codes, remember C of x belongs to f 2 power m x. So, if I say C of alpha power I is 0 for I is 1 2 to d minus 1, what can I conclude about this C of x? It should have some factor. What should be that factor?
The primitive
Primitive polynomial. What is the question? Let us say f of x is some polynomial with let us say real coefficients. Okay. Then I say for a real number alpha, f of alpha is 0. What can I say will be a factor of f of x?
1 minus
X minus alpha, right? What real number, real coefficient, right? I have a real number as a root. So, what do I know? X minus alpha will be a factor. Same thing is happening here. C of alpha power I is 0. C of x has coefficients from f 2 power m. Alpha power I belongs to what? F 2 power m. Okay, remember alpha power I belongs to f 2 power m. Okay. So, I do not really have a complicated situation when I deal with ReedSolomon code. I have a polynomial with coefficients over a certain field and I have a root from that very same field. It is not a smaller field or a larger field or any such thing, it is a very same field. Okay. Then I know for sure that x plus alpha power I, why can I write alpha plus here? Because I am characteristic 2, otherwise I will have to write minus. This will divide C of x for I equals 1 2 to d minus 1. Okay. Right. Usually you pick d to be less than n. Okay. So, like I said, it is usually much smaller than n in most codes in practice, but let us say theoretically you pick it to be less than n, which means you do not have any repetitions in the alpha power I. Okay. And then x plus alpha power I and x plus alpha power j are clearly there is no common factor between those two. Okay. So, this will imply product I equals 1 to d minus 1 x plus alpha power I divides C of x. It is okay, everybody is happy, very simple, not very simple, no, deceptively simple, let us just put it that way. Right. See, something like x plus alpha is a factor, x plus alpha squared is a factor, x plus alpha power 3 is a factor, right. So, the product of all of those things will always be factors, because x plus alpha and x plus alpha square have no common factor. How do you show that they do not have any common factor? You can use like Euclid's algorithm and try to find their GCD, you will get 1. Okay. Yes or no? Yeah, you will get 1. Okay. So, very easy to show those things. Okay. There is no common factor between x plus alpha and x plus alpha square, it is not too difficult. Okay. So this is the thing. Okay, so now let us do the same thing for BCH. Here something interesting happens. What happens in BCH? C of x belongs to what? f2x. Okay, so the coefficients are binary and the roots are from f2 power m. So now you can use your knowledge of minimal polynomials and conjugates of all these things. Not only will alpha power I be a root, what else will also be a root? Alpha power 2i, alpha power 4i, alpha power 8i, all those things will also be roots. Okay, so just because c of alpha I is 0, I know what polynomial divides c of x? M alpha I of x divides c of x. This is for I equals 1, 2, so on till d minus 1. Okay, can I write the same next step? Can I say product I equals 1 to d minus 1 x plus or m alpha power I of x? I have to write LCM here because I equals 1 and I equals 2, or alpha and alpha square will have the same minimal polynomial. Okay, so you should not keep repeating it because they have a common factor. So I can now say LCM of what? M alpha x, m alpha squared x, so on till m alpha power d minus 1 x divides c of x. Is that okay? Now I came from a code word and then I showed some c of x should have this as a factor. I can also do the reverse. Can I do the reverse? Suppose I start with some arbitrary multiple of, let us say for the ReedSolomon code, if I start with some polynomial which is a multiple of this guy on the left and has degree less than or equal to n minus 1. Suppose I have a multiple of this polynomial, okay, some multiple of this polynomial. What do I mean by multiple of this polynomial? You take some other polynomial from f2mx, then multiply with this guy, so that the total degree is less than n minus 1. So what can be the degree of the other polynomial?
Minus d, n minus d.
N minus d plus 1 is the degree I can take. Okay, so that any multiple of that you can go back and show will satisfy, will be orthogonal to every row of H, and that will give you a valid code word. So not only can you go this way, you can also go reverse. Can I do the same thing here? Yeah, I mean I can do the same thing here as well. So you take any multiple of the LCM of these guys, all of them will have definitely alpha power I as a root. But remember, when I say any multiple, can I pick the other polynomial to be from f2mx? No, I have to take it only from f2x. I can't take f2 power mx. Then what will happen? Then c of x will not be in f2x, and that's not on. I mean you can't do that, right? You want c of x to be in f2x. So this polynomial is definitely in f2x, right? Oh my god, this thing is really sticking. Let me see. Why is this polynomial in f2x? Yeah, all of these, not because c is in f of x, okay. All the minimal polynomials are in f2x. Clearly if you take their LCM, you will also get an f2x only. So that's, don't go beyond anything beyond this, just do it in f2 itself, LCM in f2, okay. So that's important, okay. That's what you should do. When you do that, c of x will have to be a multiple of that, okay, and the other polynomial which you multiply this with should also be in f2x only, okay. So you can go the reverse way also, okay. I know I did not write down all the steps of the proof, so you can fill it in if you like, or you can look at the textbooks, they will have a very clear explanation of this, okay. Alright, so what do we have now for BCH code and ReedSolomon codes? We have an interesting characterization of the code words, okay. the code word polynomials. Okay, so if you look at the BCH code, okay, so let us have a notation. Okay, so it is otherwise confusing. This polynomial I will call as G BCHX. What can we call this polynomial? GRS. Okay. So once I call those two polynomials with some name, the BCH code can be very easily characterized in terms of code word polynomials, not in terms of code word vectors, but in terms of, well, also in terms of code word vectors, but in terms of code word polynomials, it can be very easily characterized. Okay. So what is CBCH? Set of all polynomials of this form G BCH X, okay, such that, okay, so let me write C of x equals degree of C of x is less than or equal to n minus 1, okay, and then m of x belongs to f2x. Okay. All right. So if I say the degree of GBCH, okay, is something, okay, so let us say it is it is n minus k, okay, so why have I said n minus k? Because I know what will happen otherwise, okay. So let us say, suppose degree of GBCH is n minus k, okay, right. GBCH is a given polynomial, you know what it is, given a certain d you can find GBCH, you can't change that. So suppose its degree is n minus k, what can be the degree of m of x? Degree of m of x is less than or equal to k minus 1, okay, and m of x is all polynomials of degree less than or equal to k minus 1, okay. So the possible m of x all binary polynomials with degree less than or equal to k minus 1, okay. Notice there is a one-to-one correspondence. If I have a code word, then it has to be a multiple of GBCH of x. If it is a multiple of GBCH of x, it is also a code word. So the only code words are multiples of GBCH of x. I do not have to look at anything else, okay. So once I have that, I have this result. Now what is m of x then? M of x is m0 plus m1x plus m2x squared plus so on till mk minus 1, I am running out of room, so I will write it in the next line, mk minus 1 x to the power k minus 1, and each mi is in f2, okay. So how many possible code words can I have? 2 power k. So what is the dimension of the code? So this implies size of CBCH equals 2 power k, and then dimension CBCH equals k. There is a subtle point I have to show here. I have to show that CBCH is actually a subspace of F2n, okay, and that is not too difficult to show. Okay, you can start at the definition and show it is a valid subspace. You take any two code words here and add them, what will happen? You will still get a valid code word which satisfies HC transpose is 0. Okay, so it is not a problem. You can show it is a valid subspace. So we can go from size of CBCH to dimension without too much trouble. Okay. All right. This is for BCH. Okay. BCH is a little bit more complicated, but ReedSolomon is really easy. But so we will see some examples for BCH before we come to ReedSolomon. Okay, because the ReedSolomon code will have a much simpler description than the BCH code. Okay. So, the question is, given n and d, how will you find k? That is the question, right. So, the answer is hidden in this result. What should you do? Given n and d, how will you find k? Yeah, first step is to find g BCH of x. Okay. Once you find g BCH of x, what will you look for? The degree of g BCH of x, and that is simply n minus k. You simply do n minus that, you will get k. Okay. So, let us do that with f16. Okay. So, I will take n to be 2 power 4 minus 1. Okay. And remember, we wrote out the list of conjugates for this. Okay. So, that will be useful. So, but anyway, so we will see how to do this. Okay. So, let us look at d equals, okay, d equals 2 is where we have to start, right. D equals 2 is where we have to start. Okay. So, let us start at d equals 2. In this case, g BCH is what? So, alpha belonging to f16 is primitive. G BCH of x is LCM of what? M alpha x, just that, right. Okay. So, it is equal to M alpha of x. Okay. So, what is the degree? 4. Okay. This implies n minus k equals 4 and k equals 11, right. N is 15, n minus k is 4, k is 11. Okay. So, remember, you do not really have to know what M alpha of x is to find the degree of M alpha of x. What will be the degree of M alpha of x? The number of conjugates of alpha. That is the only thing you need. For that, you only have to repeatedly square alpha till it repeats. Okay. So, you do not have to do any f16 arithmetic to find the degree of M alpha of x. For what should you have to do necessarily some f16 arithmetic? To find exactly what g BCH of x is. Why might you want to find exactly what g BCH of x is? Let me see, all of you are giving me very abstract answers to find the code. To actually implement the code, right. If you want to find the code word corresponding to a message in actual hardware, right, you want to get out the code word, you better know what g of x is. It will give you a very simple way of doing it. All you have to do is simply take m of x and then multiply with g BCH of x, which in this case it is m of x times x power 4 plus x plus 1, which is a very easy multiplication that you can do. M of x is of maximum degree what? Degree 10. So, you take the polynomial and multiply it, you can implement it very easily. Okay. This is this. Okay. So, running out of time. So, let me quickly do d equals 3. Okay. For d equals 3, you will get g BCH of x to be what? LCM of m alpha x and m alpha squared x, which in this case is exactly equal to the same thing as before, x power 4 plus x plus 1. Okay. So, you again get k equals 11. In fact, you get the same exact code whether you pick d equals 2 or d equals 3. Okay. So, it is not a problem. From d equals 4, you will start getting something interesting. Okay. So, in fact, you can show that show a very general result. We will come back to it. Okay. I am really out of time. I do not want to do anything now. So, we will come back and pick up here after how many weeks? 2 weeks. Okay. So.